how to complete a problem such as this problem from number 1, using rectangles, find an estimate for the area under a curve. We found the estimate for this funny shape, yellow highlighted area by doing 2 triangles, and we got that came up to 8.5 units. And then we did the same problem with 4, I think I just said triangles, and of course I meant rectangles. And then we used 4 rectangles and got an estimate of 8.625 units. What we eventually move into is using the sum, or rather the limit of the sum of all of the rectangles, where the number of rectangles is approaching infinity. So the limit, as the number of rectangles increases to infinity, the sum of all the many rectangles. Eventually what happens is these rectangles become so thin, it's like a line. It's really just a line. So the area of that line just becomes the height of the line. And early sections of the unit is transitioned from finding these nice precise rectangles, which gave us an estimate to the area under the curve, up to using the summation of a bunch of rectangles, up to writing that as a limit. And eventually what we said was we defined a limit of the sum of a whole bunch of rectangles as the integral. In this case, it would be the integral from x equals 1 to x equals 3. So if we jumped ahead to where we eventually get to with this problem number 1 on the review would be from x equals 1 to x equals 3, integrate x squared over dx. Let me show you one other way to see the integral. We could see this integral as a sum, so this integral sign looks like an S, and if you go back, not even that far, just 1800s, if you see old writing, you'll see S looked like this. It was much more elongated, and that's exactly where this integral comes from. It's the sum of all the little rectangles. And so what's the sum of all the rectangles, x equals 1 to x equals 3, where the height of the rectangles is x squared, and the width of the rectangles is dx. And that dx is getting smaller to the point where it's eventually non-existent. Not a 0, but so thin that we don't actually need to even use it. Well, when we get to problem number 2 on the review, we've got this. Suppose that f is integrable, and that we have f of z dz integrated from x equals 0 to 3 is equal to 3, and integrated from 0 to 4 is 8. Find the value of these different integrals. So this is really a very easy problem to do if you understand what those integrals represent. So let's start with that. Instead of just looking for steps to follow to answer this question, let's look at what it's asking us to do, or what it's telling us. What this telling us is that if we had some function, let's make it this blue function, f of z, and we integrated from 0 to 3, x equals 0 to 3, that value is going to be 3. That's like this orange area here. So what we're told by this, what's in the orange box, what that's telling us is the area of the curve is equal to 3 square units. Now if we did the area from 0 to 4, we're told that the area is 8 square units. So that's another way of interpreting what the two integrals that we're given when we're given the integral. Do you see how we could find f of z going from x equals 3 to x equals 4 using these two values? If you can comprehend that this is an area. So we've got the 0, like this green area, the area that has these green lines through it. And from 0 to 3, it's this orange area. This piece on the end here, this pink part, is the part that's green but not orange, is going to simply be the whole area, so the green area, minus the orange area. So if we took the green area and subtracted off this orange, we'd be with this pink area. And that's how you complete the first problem, the part A, that says find the sum of all the little rectangles from x equals 3 to x 4 of f of z dz. Find the area under f of z from x equals 3 to x equals 4. It's simply 8 minus 3, because we take the area of the green shape from 0 to 4 and subtract the area of the orange shape from 0 to 3. So we get 8 minus 3 is 5. And that's all there is to it with this example. Example B, or part B, simply relies on an important fact to know. And here's the fact. If we reverse the endpoints, if we say instead of going, and here, let me interject here, that this is where we kind of lose the idea of area under a curve, because it doesn't really quite any longer. But if we wanted to find the area from x equals 4 to x equals 3, it's almost like going in reverse into a different dimension and finding this backwards area, finding the area from x equals 3 to x equals 4. What we're saying is that the integral, if we integrate from x equals 4 to x equals 3, so going backwards, what we do is say that's equal to the opposite of the integral from x equals 3 to x equals 4. So this is just an important fact to know. Just remember to be able to apply that if we reverse the indices, so if we integrate from 4 to 3 instead of 3 to 4, these are opposites of one another. So we get the opposite of the integral from 3 to 4. So we get the opposite of 5, or in other words, we get negative 5. Let's try and squeeze one more problem into this video, and let's look at problem number 3. Problem number 3 asks us to evaluate the integral from 4 pi to 5 pi of theta d theta. Here's what that problem would look like. Let me explain the steps here. If we integrate theta, then the integration is theta squared divided by that 2. So we take this implied 1, theta to the first power, and we increase that 1 by 1 to get 2 and divide by 2. And we're going from theta equals 4 pi up to theta equals 5 pi. And the process for doing this is to subtract what we get from letting theta equal 5 pi minus what we get when we let theta equal 4 pi. So all here is inserting a 5 pi in for theta, inserting a 4 pi when we get in for theta, and then subtracting those. Notice you'll need to keep in mind that it's all top index, ending index. So this is saying we're going from 4 pi to 5 pi. So we start with the 5 pi and subtract the 4 pi. And that's similar to what we saw in the last. Let me pull that back up. If we wanted to find the area from 3 to 4, we found the area up to 4. We subtracted the area up to 3, and that gave us this area in the middle. So that problem, problem number 2, leads us right into this problem number 3, where what we do is we say that this total is going to be the area under the graph, under the function, from 0 up to 5 pi. So that's when we let theta equal 5 pi. And then subtract from that the area when up to 4 pi. But all we do is we integrate to get the theta squared over 2. And then we substitute in a 5 pi for theta, substitute a 4 pi for theta, and subtract. I've shown the arithmetic here, and I hope that that helps. Let me point out one important, not even algebra, but arithmetic piece. Notice that we don't have 5 pi squared. What we have instead is 5 squared pi squared. We've got to square that whole 5 pi. So we're squaring the 5 and squaring the pi to get 25 pi squared. Square the 4 and the pi to get 16 pi squared. And when we calculate their difference, we get 9 pi. I hope that this helps. Problems 2 and 3 from the review.